And we are live again. Say hello. So, today is our fourth episode number 4 of building and Gameboy Emulator with Rust. So, yesterday we got some real good stuff done. So we started to well, let me just move this show hide. Oh yeah. Okay, so yesterday we start building this let me go to my okay. Okay, so yesterday we started to decoding our first instruction. So from yesterday to today, I just made one little refactor here. So this is our main loop where our CPU. So we load the ROM file to the memory. And then I think it's still. Now I think it's better. So we load the file to the memory, and then we start decoding the information. Right, so we start decoding here. Which I think So we create this new CPU. So the CPU is just a collection of our registers. Our registers are these registers that we already saw from the other documents. So we already implement this stuff. So then what I did, we started running our instruction, right? So interesting. Actually, I lost what I did because I didn't save. So let's do it again. So this is we read the instruction byte a byte, and we are doing something like this. Let me close this. So we are doing this. Okay. So from this the page summary. Okay, so here we have our commands to us to implement. So as we are reading, oh, let me open our guide. Yeah. As we are using this ROM, let me increase the size of the font here. Let's put. Okay, so we are reading this one. So our first opcode was 31. This is why we starting doing this LD, because from our opcodes here we have so 31 LDSP. So we know that this is an LD, and also from this document we know this is a 16-bit load, so not this load, but 60-bit loads which is this. So here we are. So we prepared this match stated to match one of these opcodes. So 1, 11, and do this. So any one of these will go to the match and then get the immediate 16-bit value. Invert the position because it's a big endian to get the 16, and start it in SCP because this is the 31. Okay, but I was thinking something because I was reading this documentation here. I was reading this, and this is a tutorial on how to implement this in JavaScript. So I was reading this, and then I found that actually I was reading this. I was trying to research about interrupts. So I get this. This is the flow, right? We need to every instruction when we are executing instruction, we fetch the instruction, what we did here. We decode the instruction, what we are doing here, and then we execute this instruction. So we can do this more in a rusty way, let's say this way. So what I'm thinking here is creating. So let's start separating stuff here. First, I will. So first, instead of calling this, it calls. Instead of calling memory, I will call this stuff memory. Instead of memory, I will call it MIMU, like memory management unit, because the memory is what is inside, right? And the methods are the management of it. So I think it's better. So let's see if it's still running. Yeah, it's still running. So now what I will do, I will separate this CPU and the management in their own file. So let me create here MMU. Okay. So I will get this, put it here. I think I need to use mod MMU. I don't think so. Use. Oh, I think the name of the file, sorry. So the name of the file will be MMU. Okay, this will be, I think I need to put this mod MMU, and then I put this. I use MMU. Oh, MMU. Is that true? Is that right? Yeah, it works here. So if I use, I should be able to do like use. Yeah. So MMU is now here, and it should be okay. Still working. So now I split this CPU as well. CPU. Okay. So you get CPU and put it inside CPU. Right? So now mod CPU and use CPU. Okay. So let's clean up this. Oops. Oh, of course, because CPU also use MMU. So use MMU. Why not? I think I need to create this as a lid. Mount menu, mount split. And then here I remove this. Yes. Nope. No. So I think this will work. Wait. Come on. Yeah. Okay. More CPU. Okay. And now. I think I need to learn Rust. Bulk modules. Okay. So modules. Okay, modules. Okay, so it's because I think I need to put memory. What CPU? Wait. How to more. this we don't need, I think so. Okay, we don't need. Wait. Too fast. So on CPU. Okay, so here we have now. So you keep it complain about unexpected goes to it, okay? Because not found in this scope. Which scope? In CPU. Okay. So if I do this, oh, I think I need to do this. This is where I think the hero needs to do this again. No. When models get loud, you want to move the air on this red fast one. Here. Split the program into main and leave move a program line should leave as long as your command line person remove. When a command person, okay, so this must be the main. Call in the command person line. Okay, wrong. Leave. Let me do this one thing here. So I think I will lib rs. Okay. Then in the lib I put mod CPU mod okay. In main I just put, I don't need to put anything because it's already there. Okay, so when you can do this, use use create grep. Okay, so okay, it creates an application. Okay. Here it's only extracting, but it's still here. Extracting is still here. Extracting is still here. Improving result. Okay. Okay then. So we are probably, let me delete this first. Okay. So now we don't have those files. We only have main, okay, and CPU. Import. That is what I was talking. Okay, because okay, so because the name of this project is GBRustEmu, GBRustEmu, Gameboy Rustemu. I can in the main use then what is here. Now I think if I do this, let's do this now. Now I do mmu dot rust. Okay. So now, and then I copy what is here. Here. Okay. Okay. And in the I say mod. This is equivalent of explaining this, I think so. This, I think it will still run. No. No, because, okay, so then I need to do pub use mm. Okay, then I can do this. Okay, then it's still working. Now I can create CPU and copy all the contents of CPU here. It will not work. Okay, because I don't have mod CPU here. Okay, then in CPU I don't have. Okay, now here I think I need to use the same use create a mu. Oh, use CPU. I do this? Oh, I can't do that because this. Okay. Okay, then it works. Yeah. So I need to it and publicly export this. Now it works. So now I have CPU. Okay. So now we have this run instruction. We are running here. So what I want to do here is checking if let me do something here. Maybe. Okay, so then we have this instruction. So now we are ready to decode the instructions in a right way. So we already decoded the very first instruction, which is the one. But now I get the point where I was. I want to create a new like instructions. Okay, and this will be an enum. Okay, I don't need to do this in a separated file. No, I will do. Okay, so I will do this in enum instructions. Okay. Our instructions are these, like LDBC, and it takes an LDDE and also 16 LDHL and also take 16. Okay, and our LDSP 16. So all this. Okay, I think we will need to handle. I think we will need to handle these cycles later, but for now. Okay, So I have this. I will mode instructions. Use instructions. Okay, it's not public. Okay. Oh, another follow. Oh, thank you, Goku. Thank you for following. Welcome. Thank you. So we are building a Gameboy Emulator here with Rust, or trying to build, but we're gonna build. Don't worry, we get there. So now I will. Now we can do something here. So I want to do something here. I want, like I said, I want to do this flow: fetch, decode, and execute. So we are fetching the instruction. Fetch, because we are reading from the memory, because in the ROM is there. Now let's do the decode. So we don't know the instruction yet. We just know a byte, right? Because it's not an instruction yet. It's just a byte. So let's, if this byte is an LD, I don't want to execute. This is the execution part. This is the decoding part. So what I will do, I will do something here. Actually, I will create a function called decode, which will it will receive a byte. Oh, you wait, of course, and it will return an instruction. So this is not an instruction, it is an instruction. Instruction. So this is an instruction. We will. Okay, so it will return an instruction. Which I just ported. Okay. Okay, so now I need to return. Okay, let me create one instruction. There is one instruction, it's called NOP, which is this, no operation. So here I can, like, if I return an instruction NOP, okay, so now this function is okay. But what I want to do is match byte, and I don't want to return nothing. I want to panicky. Panic is better. So I want to panic during the decoding and recognize it instruction and recognize it byte, which is this byte. I know there's the PC, and I know that there's the, because I'm in the CPU, right? So now that I'm here, I can grab this part of the code. What is wrong? What is wrong? What is wrong? What is wrong? Oh yeah, what is wrong? It's that I'm not returning. No, okay. Now I'm returning something. But I don't want to return. Okay, so what is this part? So as I said, this is decoding. This is not decoding. This is reformer. So we know this is an LD, and here, now that we have this LD, we will just return instruction LD SP containing this. Oh, sorry. Okay, so now we have this. Okay, and also here we need this because it's not exhaustive. It will complain about this. Okay. Oh, here we need also to have reference to the memory. Sorry, it's not called memory. It's a reference to MMO. So now we can read the bytes. We can call it MMO as well, right? So now we decoded this, and so we don't need. So here for decoding, now we have an instruction. Instruction, it comes from self decode a byte using memory, but I will call this variable MMO. I will need MMO to access the memory. So now I have the instruction. So I don't need this anymore. So I don't need this. I don't need this, neither this. Okay. Actually here I will execute. So let me create another function execute, which will receive self reference to the instruction. It could be an instruction and MMU. It will return nothing because it will execute. So then we get this and put inside here. Now we are actually executing the instruction. So what we do is, if this is an LDSP with my D16, no, sorry, match instruction, it's red there. This part is red on. Here we just match this instruction. If it's an instruction here, actually I need to put a note. So yeah, okay, I need to have this panicky here because, so let me do this. Okay. Okay, what's wrong here? So oh yeah, as we are getting an reference here, I need to dereference this guy inside, and then it seems to be okay. Let's see. No, I think it's missing something. Okay, oh yeah, here. Oh yeah, I have one more. Okay, here is not a byte anymore. Here is instruction, because now we know which instruction. So we are not decoding, we are executing a recognized instruction. Oh, here it says, what is the problem here? Okay, it's saying, oh yeah, because this should be this way. Yeah. Okay, then now we need to do this. Then we do just self execute the instruction passing MMU. Okay, we pass a reference. And we are not returning anything. Yeah, we still have that. The coding recognized this. So yeah, we are in the same place we were, but with semi refactoring. This is great. This is great. So what we did so far, so now we have our instruction set. I mean, not entirely done, but we have this where we can do. We have inside our CPU, we have our registers, and also we have our decode and execute and run instruction. So for run one instruction, we fetch, we decode, and we execute. We decode. For decoding, we will get the byte, which we fetch. We will match to see if that is one of those valid memories. Perform what we need to do. Actually, here I can do this. Look. Prepare some special variables. So now if we need to use for any 6-bit load, we have this, we already have this, and we can use here any part here. So here we can do this now that we already know. We can do this. So if it is 01, it will return LD. Okay. If it is 11, it will return. Sorry, LD DM. And if it is 21, it is our HL. All with those. Okay. So now so now we have all this. Let's see. Okay, let's go next to the next instruction. AF. Let's see what AF does. AF is a short, I think so. Yesterday we saw A. F. Char A. Okay. So AF is a char A, and it's yellow. Yellow is 8-bit arithmetic. So here in our document, it will be an 8-bit ALU. So here we should have char. Okay, logical exclusive or and. So we do a char with the register and save it in that register. So AF is a char. So let's write it here. It don't need it's only get okay, so let me do this. So this is first and this is second and. Okay, I can use it separated. Yeah, of course. Okay, so I think I can do this. Let me see if that is the case. So I can do it will be char A, char B, char C, char D, char E, char H, char L. Okay. We also have this char. This is a special one. This char 8L and char. How can I call this? Can I do this? No. Char. EE. How it calls here? E. Oh, char D8. Okay. Then it gets an D8. Actually, an U8. The second, the following, the anyone in this case. So okay. So now we can get back to our decode. So we have this now. AF could be no. Char could be AF, or char could be A8. Char could be A8 or A9 or AA, AB, AC, ACDC, AD, or char could be AE, AE, or even E. Then what we will do, there is no panic here because well, always should have. So we can do this. Sure. Thank you, Rust form. So now we have this. We already have N1, right? N1 is the next byte. So now we know no, I did wrong. I did it wrong in this case. I did it wrong. Yeah. It's just this. Yeah. Oops, A49 is char D, char K, char what, char E, char H, char L, char HL, and this is a special one, which is char with the first, which is here, it's there. What happened? Why I can't do this? Oh, okay. What is wrong here? I still need this here. What is the problem? What? I think it's missing something here. Okay. Oh yeah, actually I don't need this. I don't need this variable. Only here, because here I need to LD could be a lot of stuff. And I would like to check that. Okay, so then okay, so now if I execute this, it says, okay, decoding is already done. Now executing is not done, so it don't know how to execute this char. Let me put another music. Let me put something like maybe this. Yeah, this is better, much better. Wow, 1 hour already. So nice. Now, so with this, now we have the instruction decoded. We need to execute. So let's execute. Execute this here. So, well, we are not execute all the others. I will execute later. But let me, so now if the instruction is instruction char A, what should I do? First, I know that this is just 8-bit, so self PC 2, right? Because one is the instruction and the other is the bit, the byte. And I need to do a char. I need to do a char of the register with the register A and store it in A. And in this case, it's char and A. So I think it's self A equals to self A. Yeah, and it will become, I think char is difference. Char just char gate. Char is difference. Yeah, so it will remain 0. So it's 0, it will remain 0 after this execution, and we will, okay, let's do. Okay, so we execute, and now we are decoding a new LD, not to recognize it. Okay, let's see here in our, so we did this, and now we are doing this, another F. So we already know that we need to decode it here. That is this LD. This is interesting. Oh, sorry. Not LD. This decode FF. What is the FF instruction? Is that true? Is that correct? So FF instruction F is reset 38. Let me see if this is correct. Okay, so here, because somebody already disassembled disassembled. I want to be sure that I'm doing this. Okay. Here. So char A, it's correct. But now it's LDHL. So why we are not LDHL? Let me check. LDHL. LDSP, LDHL. Okay, it should be 21. So okay. Here's the thing. For the for that char, we don't need to. Oh, we need to set the flags as well. Okay, two things here in this char. One is we need to go only one because it's just AF. There is no immediate, nothing. I think we only have this. We can. Yeah. Here, char AF. It's only one. Here, this is the source of through. So I need to just do one program count. So yeah, if I do this, now it will don't know how to execute LDHL and this guy because it's this. Okay, so now it's right. Now we go. Oh, but before that, I forgot to do one more stuff here. Now these flags. And the central process unit registers, special registers here. So we have this F register, which is an 1 byte, of course. Over here. and it needs to have I need to set these flags in every operation. Stack pointer are self-explanatory. The stack pointer back to F register. The F register can't be used as operand as arithmetic logic unit and load operations because the register is reserved for ALU flags. So the arithmetic logic unit can set 4 flags in this register: Z and HC. So Z is set when the result in 0. Subtraction. Okay, so in this case, if this result is 0, then I set this set to 0. Okay. And otherwise, it will have set result. Set means 1. Reset means 0. Okay. So set in case this case. So in our char, I need to do this. Self A goes equal. Okay, so okay, first let me do something here. I will do simple one. Self A equals 0. Self F equals 2. Okay, I need to always reset the others when I do this. Reset. Yeah. So I think I can safely do this one, and because it's the first, so I think I can do this 0 0 0 0 0. So 1 2 3 4 5 6 7 8. Yeah, because it's yeah, that's it. Maybe it is not the clever way, but it's it. So it's very straightforward. And what is the other document says? Meta operations, yeah, this match operation. The lower number is always there. Okay. Match operation used subtraction. Match operation raise it kernel do not raise it anything. So yeah. So char should be always this way. Okay. Okay, now we go to the LDHL. LDHL, it's here actually. Okay, so LDHL, we already know what is LDHL. Let me get there. I will implement all LD. So LDHL put the value NN in this. So how we will put 16 value? This is interesting because now I have HL, which is two different registers, and I need to put a 16-bit there. So I think I put the first byte in H and the second byte in I think so. So let's do this. So instruction LDHL D16. I need to put self. Okay, so I know that this is like above because it's LD, and I need to put self H like just the first. How can I get the first? This is 16. How can I get the first? So I do this 16. Okay, let me do something here. Print. Oh yeah. This 16. Okay. It will go to other, but I will go to see here. So 09FF. So 09 should be. Okay. How can I extract this? I think if I do this. It will appear 09, right? 09F. Just a second. FF. Okay. But in this case, I need to do 8. I think it's this. No, the other way. So, okay. Yeah. So here we have HL. So we do the self H equals to this. I think so. Without this. What's that? As U8. And self L as without this. Okay. Okay, so we have it here. It's set. PC is already set. So yeah, don't need this anymore. Okay, now I think we can do also DE and BF because we already know how to do that. So let's see BC. It's the same, but here it's B, it's C, and here it's D, E, D, E, and E. Okay. Oh, it's not C? Oh, wait a minute. A, B. There is no C? Register. Oh, it's missing something here. Oh, yes, there is a C. Register C0. So it's 1, 2, 3, 4, 5, 6, 7, 8. C, D, and E. 0 as well. Oh yeah. C. Why I miss those? Okay. So now it is there. Everything. So we already did all this LD. Okay. So let's see. What is the next instruction? 032. 032. Okay. So 032. 032, 032, 032, 32, 32 is an LDHL minus. It's an 8-bit load. 8-bit load. This. What this means? Same as LDD. Okay, so all those three. So all those three are the same. So let's create this instruction. So LD, LD, so LD, LD, HLD, A, or LD, HL minus A. LD D H L A. So LD HLDA, LDH minus A, all then are the same. So here we are. So all the same opcode. So if all are the same opcode, it doesn't matter. I will do this HD LDD HL. Put A into memory address HL decrement. Ah, yeah. Is that this is the special instruction only made in Game Boy that it decrement. Okay, So let's go there, and it's here. So if it's 032, it will return instruction LDDHL. Okay, if you execute, it says LDH1. I don't know how can I execute this. Okay, and then don't worry, my friend, I will teach you how to execute this instruction. So LDH, what we should do, we should put A into memory address HL. Okay, so now, now I need to get HL as an, so let me do something here first. And I know this is an 8-bit, so if it's an 8-bit, which is saying here, I need just to increment my PC for 1. Let me increment my PC here and do some debug. Println, oh, what is println and what I want to do, I want to, because I want to see what is in self H and what is in self L and what is inside H and A. Okay, so H, L, A. What's that? Oh, well. Why did that? Why I did that? Okay, so continuing here, what I did. Okay, so 8 is 9F. So I put A into memory address 8L. So the memory address will be 09FF, of course. So how to put that? How to put those HL again together? It will be, so let HL equals self H. I think it will be something like this. Self H let me do something here. If I do this and do this 8, what it will be, it will appear. Wait. I think it's this way. So I need to do this. And I think if I do oh wait. Okay, this is this way, but I need to put the other way around, I think so. Wait. So now. Okay, so now we have 099 and FF. I want to put this. So I need to put how to put it there. Back. I did. Oh yeah. Sorry. This way. So this way, if I do this, 0 F 00. Sorry, this. Is wrong here. I think this is maybe okay. So may action is as use 16. No. It should have no. What up? Okay, actually here I need to do this. Okay, that's back. Okay. Let me see if I understand. doing this right? Oh, of course. Okay. Okay, but this is not the way I want to do. I think it's just this. Okay. But what if I do this? Actually, I think I don't need to do this. Finally. Okay, so then we have this. So I think we can do this. Yeah. Now I have HL back, so now I can put it back. So I can self. No, I can do mem write. Mem write address HL. And the value of self A. Okay, so I put self A. Another follow. Thank you, Reader Cass. Thank you for following. Appreciate that. We are building this Gameboy Emulator here. So we are okay, so now we just write this, put A into HL. Now I need to decrement. So this decrement, that decrement HL is something else, I think so, because save. So, okay. So deck. So this is something that I need to understand. How can I decrement a register? It's just an integer operation. Oh, I think it's that, right? Just like that. That's a decrement. I think it's oh, I think it's just it. So I do this and I do this self age. Actually, I need to do this. Ah, there's one thing here because I need to increment LD, right? I need to increment HL. So I do this. And then I need to do the same I did here, which is HL. I think so. Let's see if it works. Okay, H now is different. Yeah, because I was decrement this. Let's move to this print. Oh, it's decrement actually. No, then it's changed because yeah. Yeah. Okay. So then we are CB. We are in the next iteration, in the next instruction, CB. So let me. So we did this. We are here. Oh my gosh. Okay. We have a lot of instructions to implement, so I think this is a good way for doing this. CB. Let's see what is CB. CB is it is C CPE 1. Okay, 1-bit load CPE 8-bit load CP 8-bit L. Okay, CPE. No, but this is not CB. Oh, I got the wrong. Got BB. CB is. Oh, wow. Ooh, we start this CB stuff. Yeah, this is a prefix stuff that we have all those all their opcodes here. Great, but that's great. It means that it's till here is okay. So prefix CB. Let's see prefix. Command. Oh wait, that LD. Something with the no. Okay, but where the CB? Okay, CB. Oh, then I think it will be something like this. Wait. When it's CB, then it is here. CB, then the next opcode, and then the immediate. So how can I do that? Well, I can first set this. I don't need to do this. I do this directly in the decoding. So if it is if it's a CB, then I still need to get the byte. Then I need to get. Okay, so let me do this. I will also let in case of prefix CB and N is opcode, so let CB opcode equals to N1. N2 is N1. So let CB N1 be N2, and CB N2 is more 3, and CB 16 is the CBN2 and CBN1. Okay. Then I think it's right. So then if it's this, okay, then I can go into, so then I can do this panicky. I do another match here, match CB opcode. I don't like the music, just said. Okay. So CB prefix. See if that is true. 7C 7. Wait, 7. Where's that? Ah, yeah. we are doing great. So yeah, we are doing great. We are doing right. So then I can do this. Beat 70. Let me go to the beat 70. Think it will be here, comma, speed CB 7C 7. It says bit 7 8 bit 7. Oh, bit. It should go 1, 2, or so 3, or just 1. So it's bit 7 8. So it's bit 7 8. Okay, so this, okay, so let me do bit br. Actually it's b bit b a bit b b bit b c bit b d bit b e bit b h. Get this. Bit b bit B, bit B, E, bit B, H, bit B, H, L. Then here, if it is 0, 7C, 7C, it's bit 7, 8. So a return instruction bit oh actually it have a bit like an I put a bit. Okay, I think, yeah, it's red. Yeah, it's late. So we decoded the CB. We are already decoding CB stuffs from this. So let me just recap what we did today. We have factored our previous now is have separated MMU, so memory management unit, CPU. Now we have an ENU with all instructions. In CPU we have our fetch, decode and execute flow very separated. So we fetch from memory, we decode the instruction. For decoding the instruction we have this some preparation here to get the immediate bits. Remember here that we have this, so we get these immediate bits in case of prefix CB. We have CB, and in case of not CB we have the immediate 8 bits and immediate N. We also flip this because it's, as I said before, it's an big Indian. So then we also do the same here for CB. Then we enter here and we start in decoding all the structures. We already decoded some load, some chars, and we get this CB. CB are the prefix. So we have this. This is the master instruction set, but it has like a 244 instructions, but it also have a prefix here, CB, which open other 255 instructions. So we have this match here as well, and we are starting the code. This is like bitwise operations and so on. So we are operating here. We already have our shore. So then we go from this decode. We get the instruction because we get this enum, and we go back to execute. Now execute is match against the instruction. So if a load, we load. If it's a load SP, we load in there. If it's a load DE, if it's load at HL, load BC. We already did load and load HL and decrement HL, LDD HL. So we load and then decrement. We also did a char A. For char A, we need to set our flag. We already did this, so I think we are good. We are good with the flags. We are good with the char. Of course, there are many more opcodes to implement, but for 2 hours of coding, it's good. So thank you everybody, and I thank you Chris Biscard for writing me. That's nice, thank you. So yeah, so thank you for watching, guys. See you on Monday. So I'm not planning to stream on weekends, except when some special weekends. If I'm working outside my city or something like that. But otherwise, I will get back only on Monday night. So good weekend for everyone, and see you on Monday. Thank you for watching.